think I have to press start twice or something. Okay, I got it. Oh, that's so cool. Wait, I don't know if it's going. So if you're absent, I'm sorry. We'll see if it works. I thought it was. It kind of looks like, I don't know. We'll find out. Test to see how bad of a cameraman I'm. So how many people don't know the answer? So shout it out on 3, all right? Everybody has to shout it out. 1, 2, 3. Oh, you guys are awesome. Okay. That's so awesome. Oh. Yes, the heliosphere. All right, so if you guys can remember the heliosphere, you're in good shape. So the heliosphere is defined by the orbit of Neptune, just a quick review of where we left off. And so the Kuiper belt out there, you don't really have to know that. You don't really have to know that. But if you can remember that the planets are density stratified, that's really good. Right? We kind of went over that word stratified. You guys asked, like, what stratified means. Does anyone still have a question about that? If I say that the solar system is density stratified, does it make sense to you? It's kind of got layers, right? It has some kind of organization. Heavy stuff is here, light stuff is here. Right? And today, I want you to connect back to the Earth. The Earth is density stratified. Heavy stuff's in the middle, light stuff's up here. That makes sense, right? Like air is really light, right? So in the middle of the Earth, there's a lot more heavy stuff. All right. Okay, go. All right. Oh, I don't know where to put this little guy. Let's put you down there. All right. And so I asked you guys to draw, and you guys did a good job, and I'll give it back next week. The outer ice giants, so these two are ice. The gas bags, Jupiter and Saturn, not quite cold enough to actually make ice, so they're more gassy. And the terrestrial, the rocky planets, Mercury, Venus, Earth, and Mars. All right, so we have some kind of density stratification. And know where the asteroid belt is, and you guys did that. Asteroids here, comets out here. And so I was asking you guys explain the difference between a planet, an asteroid, and a comet. Everyone seems to do that. Is anybody still not sure what the difference is? Yeah, so what's the difference between an asteroid, write down in your notes, an asteroid, a planet, and a comet? Let's get to those things. And this is a hint. Asteroid, the definition's up there. All right, so if someone asked you, okay, why do we call a planet, an asteroid, can it be the same things? Are they different? When asteroids hit Earth, they're meteors. And this is what we have outside of 118, the lab. Right.
Where did it hit?
I don't know. I think that it should say on the description there. We can probably see. I have a picture of it later, and I'll see if we can zoom in and say. So we actually get a lot of meteorites from the poles, and you'll probably see why today when we talk about the magnetic field. So some places have stronger magnetic field than the other. So the poles, ice, that tends to preserve them. So if you're willing to be a glaciologist and go up to the pole, you can probably find meteorites and really famous.
That's a good question, real quick. I just want to show you something.
Yeah.
It seems like I'm signed up for 2 EES. Mendoza, is that you, right? Is it on your blackboard?
That's the wrong lab. It should be with Casey.
The second one is with Casey. The Thursday one, who gets that pop up.
So yeah, that happens to me too. Like you used to have the other lab on there. You get like all the notifications.
Oh, so Blackboard is in sync real time with PeopleSoft. So okay. Blackboard is behind.
Okay.
And that's why. So if you might see that there are times that you're still in classes on Blackboard that you know that people in my Fresno State says that you're not in.
Okay.
They update PeopleSoft after. It's not real time synchronized.
Okay.
Yeah, and so I'm sending emails to students and they're not in my class. And so thank you for pointing that out. I always forget that. Yes, Blackboard is always behind PeopleSoft, which can be a problem, right? It's anxiety. It's like, what the fuck?
So should we be getting notifications from Carrie Portman? I mean,
She has oversight of ES1. So if it's relevant to her class, no, but if it's for like all the sections, I would say yes.
like assignment 1 was like
Oh, no.
yeah, I'm getting that.
Okay. You're probably still in her class. If you don't see my section, so if you don't see ES1 virtual lab, and my name is an instructor in the Blackboard, write it on your piece of paper, or even if you're clicking in, write it on a piece of paper, hand it in after today, and I'll reconcile that. So I can add anyone to Blackboard. Right? So she added herself to my Blackboard. That's why I thought initially maybe, but no, you shouldn't see her assignments.
Okay.
Administratively, we have jobs available.
Good.
Software security. Jobs. All right. So I want you to turn to your neighbor and explain to them what you know the difference between these three are. And see if you actually agree, or if one of you has something that's a little bit different nuanced. I think you can learn from each other. All right, so I'll give you guys 2-3 minutes for that. So write down actually what my partner thinks is bullshit. What do they think? If you think it's bullshit, convince them.
I'm gonna put frozen gases in the water.
Good.
Mine, I just put thick water in the water.
It's really interesting why we think that.
I think it's just for
It has, so we now see with the flyby and the moon, it has the same ratio of planets, moon, and all the other planets. But there's like a constant ratio. So we think, oh, it's not planning or this planet yeah, we did do something very yeah, I was just
We all think.
Things revolving around.
Well, planet goes around the sun.
Yeah.
Going around it.
Next week's class is like the homework. She said it's
It's not a building.
No, I haven't checked. I didn't do the.
Where we supposed to
Well,
essentially, if you take a trampoline,
Yeah, but I
center of the trampoline, what's happening is all that space is now bent and moved. Yeah, so if you start.
It'll work.
Yeah, she really did. She just threw us into this.
If you get something that's real like
So if you had to explain
how
what
do I
planet
say,
was, what would you say?
geometrically sound.
Oh, no,
It's completely
So that was a good question.
kind of have a
What
less
is the planet? Like,
All
seems like everybody
So
knows the
because of the
difference between an
sun,
asteroid and a
everything
planet,
with
but
mass essentially has a gravitational something else with mass.
so we have, are all planets rocks?
It's larger, it's affected gravity.
Not necessarily.
All the.
Not all planets, but
From what I've read,
traditional planets are, yeah.
one of the definitions for planets is
They
something
seem like big, right? They seem like
Its
much
own
bigger.
gravitational energy to
Yeah.
has cleared its own orbit. And
That's a part of the solar system.
like, you're not gonna see Neptune coming in,
Look at that.
but that's fine.
Yeah.
Whereas other things may move
I
around.
like what you're
but it's
thinking.
we can't count all the stars, like, we can't count all the
More
asteroids.
than satellite orbits
We couldn't count
around
the
the Earth.
because
Oh,
Okay.
it's easier.
Like, it's like one satellite, right? We have, America has, I think, 31 satellites up in our satellite system, so they have different
We see the asteroids too, right? We see the
distances
comet.
that they are. So all of a sudden, you get these, if you don't have satellites, all of a sudden.
Yeah, but I like the way you're thinking, and that could be a definition that they're seen
Experiencing
differently in the
sublimation
sky.
from a solid
And
to
that's how
gas,
we might
losing
separate
a
them
lot of
out
mass quickly.
from the other. So that's not bad.
My
you can
understanding,
match and take it.
losing mass.
Check. Let's see,
Get
like,
like match.
Quick rate,
yeah, or like a lighter.
the orbit in turn will
So I
not
don't
We
know
thought,
if it
like,
was,
yes, I'm born and
so what do you need for the
What's,
nitrogen?
oxygen.
Oxygen.
About between an asteroid and a comet.
So I have to have like.
asteroid's gonna be
Yeah, but you can
comprised
probably
of
make other types of
rock
explosives.
material,
So
well,
if you have like a type of
and then the
reaction,
comet,
you could
it's a
probably
big,
do
it's all
that. You
ice.
just have to find
And then
like
as it gets closer to the sun, it experiences sublimation, which is the process in which a solid goes straight to a gas.
If you find that out,
Would it turn into a sun?
The thing is, wouldn't you have to have a material that puts enough like
Just
thermal
material.
output to occupy itself? So if you want to continue the reaction, you have to shift it.
Traditional, I think,
You have to have more thermal.
if it's a gas and it's solid, it's
Theoretically.
not gonna have density particles.
geometry and how
Therefore, it
that's
should
why
be
it's supposed to have different reactions that way.
So it's gonna be a dense.
Geology, planet, whatever, astronomy. We do it all.
Does it have to be like a planet has, like it's an orbit and it has its own?
Oh, that's a
Pretty
good,
interesting.
good definition
I kind of still
character.
have to.
Yes.
I'll give them
Yes.
credit.
Yes, it has this elliptical orbit around the sun,
But don't
which,
the meteors have like their orbit too?
Not
Meteor belt?
necessarily because they get pulled more by.
so they're moving around a little bit more. So they actually move and jumble out at Jupiter and come to a different, the planets don't move quite like that, and so I like that idea a lot.
Because they're bigger, they have more
They're big.
influence about the.
So it's a different interaction. You guys think, that's really
Like the
good.
way I do too.
That's the growth mindset. That's the growth mindset. So a lot of people think if they get it wrong that I'm stupid, I can't do it, I'm not good at math, I hear this a lot. But actually, there's this, okay, universities and like school districts spend like all this money to try to get students like achieving better. And if you give this article, it's really good, it's like a 5-minute read. People have done research on the brain. And they show that with practice, just like riding a bike, you don't necessarily ride your bike at first. You might fall off, but if you were really, really talented, okay, I'll give you that. But most people have to try a couple times and they have to fail. And so failing is okay. So if you don't know something, it's like, it's okay. But like, even if I don't know something, if I fail, I'm gonna like keep going, right? But a lot of people don't do that. They think I can't do math. And so the brain actually grows. And so IQ isn't fixed, which is really cool. Most science shows that now. And so you can actually become a mathematician even if you think you suck at math. And so if somebody tells you you can't do math, like a TA or something like that, just tell them bullshit. And that they're not helping you enough. Yeah.
Yeah, that's like something that my teachers used to always tell me in 5th grade.
Mhm.
Like, keep on working on
Yes.
that to really get used to it.
The persistence.
Not give up,
Yes.
Yeah.
Persistence. Persistence.
definitely.
All right, so asteroids, most of them happen between Jupiter and Mars. Comet and planet don't happen between Jupiter and Mars. You can kind of distinguish. They're big. You don't have to remember the size. And they can strike Earth. We have one. This is the one that's outside of the lab room. And she wasn't able to pick it up, but I'm still giving her points for the selfie. Right? And so this is early Earth. This stuff is the stuff that was the early solar system. Right? And so when we look at Earth today, if I go outside and like take a piece of soil and hold it up, it's nothing like the chemical composition of that meteorite. So Earth is very different today than it was at the beginning 4 billion years ago. Comets are different. So you guys got that. They're icy, right? So they're not rocky. So they're very icy planetesimals. And they orbit the sun. They have very different elliptical orbits around the sun. So instead of the plane of the planets and the asteroid, the comets have many different types of trajectories, right? So they're not in the same plane. And they develop this beautiful tail, right? Short period come from closer, long period come from further away. And just kind of know that they're like dirty snowballs. So they're these volatiles, things that turn into gas at our room temperature, right? Water, carbon dioxide, methane, ammonia, right? And so we think that we got our oceans probably from comets after the moon struck Earth, right? So they can strike Earth. And so know that the solar system formation is not the Big Bang. Most of you guys seem to know that, which is really, really good. These are two different things. So the solar system formation 4.5 billion years ago. The Big Bang, the formation of the universe, is about 14 billion years old, right? And so the universe is continuing to expand. They formed two different things. The Big Bang formed the first hydrogen and helium, right? The solar system, the sun, actually formed the much heavier elements, so very different. All right, and so how do we get the heavier elements? Fusion. So you need the stars, right? So how do you make a star? So you had the Big Bang, and you had these things called nebula. You just had these spaces of space, these places in space that were a little bit more damp. They had a little bit more stuff in them, right? A little bit more helium, a little bit more hydrogen. And we see these out in today. Do that. We see these out today through Hubble. Really cool. And what's extra cool, what's extra cool is that in these regions of space that have stuff, they look like big clouds, the mass is not distributed evenly within that cloud. Right? So these nebula, these clouds, have different amounts of stuff in different places in that cloud. And because there's a differential amount of mass, so gravity starts to work. And so let's say there's a little bit more stuff here. This can kind of start pulling stuff into it, more stuff, and pinch off and become its own new formation of a star. So these are how stars form. They form from these wet areas of space, and some part of that cloud, that nebula, will pinch off, right? And so the gravity is actually what causes these things to pinch off, and it's because there's different amounts of mass in different places. All right, so once you set that up, you can actually make this. And what you'll have is when this ball pinches off, it starts rotating, and when that rotation happens, you start getting increased temperature, so the mass is hitting into each other, and you'll start flattening out that ball. All right, and so this is how you have the first star of our solar system. So you'll have a protostar, a nascent, a baby star form, all right? And that's when you have the mass hitting each other enough that you start glowing. And we've seen birth of stars through telescopes, so we know that this happens. So the first star is born when you start getting nuclear fusion, just like you guys said. So when the atoms start joining each other and making new atoms. So you start making carbon, you start making oxygen, you start making nitrogen, right? And these are very massive, and they're very, very short-lived, right? So they tend to last for millions to tens of millions of years, right? At the end, once you have every atom used up and you don't have any more helium, you don't have any more hydrogen, you get an explosion. And this is a supernova. And this is what starts forming the iron, the lead, the really heavy stuff, right? So you need the explosion to occur to get to the bottom of the periodic table. So the Big Bang really only gave us hydrogen, helium, lithium, beryllium, and boron, the very light elements. Everything else on the periodic table comes from supernova, stars exploding, stars forming and exploding. You go up to iron in the star, the explosion, you have to actually, for stuff bigger than iron, you have to actually start exploding, right? So all the atomic numbers have less than 5. You don't have to know that, that's not too important. But all of the heavier elements are from this star formation. So nucleosynthesis is just the making of, so making, synthesis, making of nuclei, making of new atoms, new heavy atoms from the supernova, from the explosion, right? And so if you were asked this question, what would you say, true or false? Is your eye clicker stardust? Hint on any exam, if it's written, totally write it like that. Totally. It's pretty good, right? Usually we grade things really fast, and so that would look right. Oh, yeah. And if you don't have your eye clicker, just write it on your piece of paper. A or B would be fine. Or you could write like that. I think we had 28. Anybody need more time? All right, so we had a couple of people, 5, say not true. All right, but that's okay. You should say true, but it's okay to say not true. So the eye clicker, what is that made of?
Stardust.
It's made of stardust. So like, you guys know what elements?
Carbon.
Carbon, polymer, plastic, something. So carbon, you need star, right? You have to get something bigger than Big Bang. If it has metal in it, metal's heavy. So yeah, it's probably stardust. It's just really cool. Like, we were once inside of stars. That's like crazy to think about. Kind of blows my mind. All right. And so understanding this theory of the solar system formation is kind of a good starting point. And so when you get enough of the nebula pinched off, so you have the nebula, it starts rotating. And because it's rotating, it's much more stable as a flat disk. So you automatically get the solar system type of configuration. So the solar system started as a nebula, and it went pretty early on into this protoplanetary disk. And so a lot of this stuff is left over from the Big Bang. Any hydrogen, any helium we have, water, all of the water on Earth, it's all left over from the Big Bang. And everything heavier is from the star before our star. Okay. So it's kind of a beautiful theory. And so this nebula condensed into this disk, and it actually made our current solar system. And so the rings kind of stabilized over time. And so the ball at the center grew very dense and hot once again, and it ignited to form a new star. And the fusion reactions actually begin. This reignites our star, and so our current sun is born. And all of the stuff that stays in the outer reaches starts to condense into particles. So all of this stuff just starts agglomerating into bigger and bigger pieces, right? And you start getting these meteorites, these protoplanets. So these things start just increasingly bouncing into each other and forming bigger and bigger objects. And so when they get big enough, they actually form into planetesimals. So these are baby planets. How do we know the age of the solar system? Yes?
No question.
No, you're going to answer.
No, wait, what? How fast is Earth going around the sun? Is it fast? It seems slow because we're all here. Bro, it must be going fast.
Yeah, I'm having a hard time with that.
I think it's a 93 million mile radius.
I don't know the differential rates of the planets. And so we want to look at the planetary years. So how long each planet takes to orbit. That's a really good question. Actually, I didn't find that. You probably Google it right now. So I don't know if it's fast or slow. And it used to go faster. And Jupiter actually slowed us down. So that's what people kind of think. So
Jupiter slows down.
It's big enough that gravity will slow.
the gravitational pull. Those are good questions, though. How do we know the age of the universe?
Yes, universe?
Yeah. Oh, sorry, the solar system. Thank you. How do we know the age of the solar system? So Marshak says 4.5 billion years old. Google says 4.5 billion years old. Asteroids. Asteroids. You guys mentioned that last time. Asteroids. Yep. You knew what Patterson. You remember what he measured.
I was gonna tell you how fast the Earth is going.
Oh, how fast is it? Is it fast?
It's 67,000 miles per hour.
Dang, what?
That makes 18.5 miles.
That's pretty fast.
That's not that fast in the grand scheme.
Yeah, that's what I'm wondering. I don't know how relative that is. But it seems like a good speed for us, right? It's a good speed for
I'm
us.
comfortable at that.
So if we like jump out of like the Earth's like ozone system, like take off on us. How does that work?
Because you're still getting pulled to it too.
So Felix Baumgart, I'm not going to remember his name, he went up. So the ozone is about an hour drive. It's like 60 miles up. If you go 60 miles an hour, you get there now. So it's not that far away. And he jumped.
Stratosphere jump, the Red Bull guy.
Yeah, so I think Baumgart was before him, and then he came, and the guy was like helping him do that. So he stepped off that balloon and went down. So to him, he was standing still. It's a hard sensation to him. He was like still, but Earth was like moving towards him, and his balloon was like going, wow. And so everything was still relative to him. And so it's really interesting. Yeah, that guy. I just wanted to show you guys so you understand kind of where these things come from. And so this is just ages, and yeah, you guys are right. You said potassium argon. I thought it was actually uranium lead, and it's not. It's potassium argon age dates, and so they have very, very long half-lives. So you can get back to billions of years. GA is billions of years. And you can see that these are meteorites that have crashed into Earth, and these are lunar meteorites. And so we have Earth, and we have meteorites on the moon that really agree pretty well. So there's this nice 4 to 4.5 billion year old age range. And these are all done by different, these are all different 1988, 1995, 2007, 2004, 1989. So the author is showing that, you know, we have a lot of studies, people from different places getting the same ages. And so this is how we kind of think, this is how old the Earth is. This is how old our solar system is.
What about that first one, like 5.5?
Allen date, yeah. I have to look into what, so this is a special comet, meteorite. I have to look at the specifics of it. So I don't know why that's so old. That's a really good question. And these are all people who have pieces of it in the different labs. All right, and so they're actually all getting kind of this age distribution. And usually if different places measure the same thing, you don't all exactly agree. And so you would kind of call this probably that lab didn't do as good of a job as these labs. And so you can probably take the mean age or something like that, and you'd use the standard deviation to get a general age.
You can do a least squares adjustment, essentially just weight that a lot less.
You don't like throwing out data, but it's,
No,
yeah,
I didn't
why
say
is that?
for us, weight it
Yes.
less.
Yes, yes, yes. I don't like doing that either. So the age is it's like the concentration thing. Like, what's the concentration? Well, it's like you measured it 5 times, and it has some kind of and this is what we struggle with science. So it's really interesting. Well, this says different things. And so I really want you to walk away understanding that the solar system is density stratified, but also Earth is density stratified. All right. So after Earth formed, right, and it had that meteorite composition outside the lab, it actually changed over time. Right? So all of the heavy stuff, just like the solar system, all the heavy stuff goes down into the middle, and all of the light stuff, like our atmosphere, our water, comes to the surface. All right, and so all of the topography that you see in lab, this is very light stuff at Earth's surface. So topography is actually controlled by stuff, the density of stuff. So the interior is very different. It's differentiated into a nickel iron core. How do we know that?
Density.
How do we know it's nickel?
Density.
That's one way.
It's heavier.
What can we look at?
Right.
Meteorites.
Meteorite.
Meteorites.
Got it.
Yes. Yes. But yeah, so we actually confirm by density. All right, let's go what density of Earth is. And we have a very stony, so silica oxygen, SiO, quartz, is most of the mantle and the crust. All right. And so this is very rocky. And so this is early Earth. All of these meteorites crashing in. This is early Earth. All right, so this is the meteorite. This is an early piece of Earth. But today, all of that heavy stuff is in the core. All right. So if you had to explain these things, could you do it? Right? Can you compare the solar system and Earth and explain how they're both density stratified?
Yeah.
Higher order thinking, if you guys can do that, you pat yourself on the back. And then why is it even important that we have a metallic core? Who the fuck cares? Doesn't matter. If we not have it, would we be okay?
Because it's molten.
So pick a minute to think and write down an answer, and then I'll have you guys compare answers. But if you could compare the solar system to the Earth stratification, I think that's a really high order thing that most people can't do. So you're on good ground. And then if you can kind of think, well, okay, we have this core. Does it benefit us? Was there something in Marshak that he said about the core? So these would be good essay questions on an exam worth 10 points.
Oh, right.
Give you guys 3 more minutes. One more minute. Five, four, three, two, one. Compare with your neighbor. See if you wrote the same thing.
The solar system, all of it's towards the same as the
Yeah, but gives us
That's also like I think something like
for the most part.
you feel like it breaks out.
Gravity that's like for the most part pointing to displays,
Yeah, I remember having
Yeah, and then it gives you as long as that's what you say. As soon as you stop.
Did you guys compare? It's the same.
We're trying to find a way to not.
Slowing down.
So for the first one, does someone want to volunteer and explain what they or their awesome partner thought about the density stratification of Earth in the solar system?
Isn't it because like the core and the sun are kind of the same thing? It's the densest parts of the
Okay.
respectively, and then as it goes out, it becomes less dense,
Yeah.
more
Okay.
distance, less dense.
Would you guys write that?
Yeah.
Could you explain that? That's okay. So you could draw maybe from the core to the cross. You could draw maybe from the sun to the comets. That would be a good way of showing what you know. So this is probably going to be on the midterm.
Is that a good answer?
That's a good answer. Yeah. And I would draw kind of to back it up.
I can't draw them.
Yeah, you can like label stuff. You don't have to draw. And why is it important that we have this differentiation?
Because it's a a magnetic field.
Yeah, so I heard you guys explaining that. How many people put the magnetic field? Okay. Most of you guys didn't. Did you like come up with another answer? There's like some other good ones. No? Yeah.
I just hope that it helps keep the planet from warm.
So we have some heat that comes from it that helps plate tectonics. So if plate tectonics was dead, if the Earth like didn't move, yeah. So I don't know if we have an ocean. I don't know if we have an atmosphere. So not only did we get our ocean from comets, there's really good evidence, isotopic evidence that's like, okay, we got some from comets, but we also got some gassing from the interior of Earth. And so it actually provides atmospheric stuff, right? And also, what about deep sea vents? Where do they think maybe life started? Some people think deep sea vents.
Right.
Some people think tidal areas. So we can talk about that later when we go over the geologic timeline. But yeah, so a lot of people think, some probably think that the deep sea vents. And so you need heat to rise up and convect and to move crust apart, right? And so these deep sea organisms, James Cameron is out there filming, they don't have the sun, right? This is our typical energy source for all life on the planet. They're actually heated, they're provided energy from remnant stuff from the core. We can make that connection. So I would say that's a really great, important thing that it does. It gives us some kind of internal energy. And the same internal energy actually causes a magnetic field. So it's doing a couple of things. Anybody else have any other ideas?
If it stopped moving, wouldn't it slow down like our seasons and stuff too? Wouldn't it slow down
Who
the
controls the
rotation?
season? Oh,
The rotation of the tilts, whatever.
Yeah.
Not necessarily, but it would.
I don't know if that would change the
Or the tilt or
seasonality.
something.
Yeah, that's a little
I'm just
different.
guessing.
But I haven't seen anything tie the two together, but the Earth's tilt does change, right? So it wobbles, and sometimes it changes, so it wobbles, and it sometimes changes to declinity. And so those two things, we know that they change over time, but we don't know necessarily how. We just know that the wobbling kind of does that. I think that's a physics thing that can actually happen without the core, but I don't know, maybe that does play something in there.
That contributes to, the mass of the Earth contributes to the effects of gravity as well.
Yeah, if we didn't have it, we could take a we could move in really slow motion. All right, so yeah, what's really important about it and why your grandma should care, you have a magnetic field. And it also does a bunch of other awesome stuff, right? So in Marshak talks about when he says, okay, as you approach Earth, what would you like to encounter? Well, the first thing is the heliosphere. Well, another notable thing would be Earth's magnetic field. So Earth has a magnetic field. Not all planets do. And it's really important. And so if we just look at a simple magnet, right, so you have a south end of the magnet and a north end of the magnet. And from the north end of the magnet, these electromagnetic lines, these magnetic lines, go around, right? So they emanate from the north and they go into the south, right? And so this is northern polarity, this is called southern polarity, and these are all the magnetic field lines, right? So Earth's magnetic field acts like this. A lot of people understand magnet, so it's an easy analogy to make. And the field has a north and a south end. We have a north end and a south end. And the field grows weaker with distance. So as you go away, this is weaker than here. Right? And the magnet flux is directional. It's just another way of saying it moves from the north to the south. Right? So you have these lines flowing from north to south. It's a closed loop. Right? And so this is actually inside of Earth. It's really the core, but this is a good way to think of that. We have a north end at the South Pole, and the magnetic lines come out, and they flow into the south end of the magnet, which is our North Pole. So it's kind of opposite. Right? So Earth's magnet acts really just like a bar magnet. And the compass of a needle compass, when we point the needle compass, it points to north. So it's following these lines, right? So it's following this magnetic flux to the North Pole. Right? But it's actually pointing to the South Pole of the magnet. The magnetic lines extend out into space, so you can see them going out into space. They weaken with distance, and they form this shield. And this shield is really important. Without it, you'd have solar storms hitting us, and we'd have electricity going out. And so solar storms do hit, and they cause electrical outages. And when our magnetic field isn't quite strong, we actually experience these. A lot of the satellites also. And so this is a good picture depicting the solar wind, the solar storms coming, and this is Earth's magnetic field. And it's protecting us from a lot of the incoming radiation from the Earth, right? And so the solar wind kind of goes around the magnetosphere. This is the magnetosphere. And so it's deflected. And the strongest part of the magnetic field is here, where you see this part and this part. So around the equator. The weakest part is by the poles. And so stuff can sometimes come in, boom, boom. And that's what explains the northern lights and the southern lights. And so the poles have weak magnetic fields, right? Where the magnetic lines are actually perpendicular to the surface, that's where stuff can actually come in. And so that's at the poles. And so this is how you get the northern lights. So you have cosmic radiation, sun, solar stuff coming in, and it's deflected here. The equator is really shielded, and it just goes whoop, whoop, and it starts interacting with our atmosphere. So you have this energy coming in, and it's starting to excite gas in the atmosphere, and it starts glowing. And so some of these particles, energy, makes it past the magnetic belt, and they're channeled along the magnetic lines to the polar regions. And this is where we get the aurora borealis and the southern lights, so the northern and southern lights. So it's an explainable phenomenon. All right. So if you were asked on a midterm, where is Earth's magnetic field the weakest? Would you say A, 0 degrees, B, 23 degrees, C, 66 degrees, D, 90 degrees, or it's weak all over? All right, let's see. Do what you do. This will probably be on the midterm. Anybody need more time? Everybody click good? Oh, we got 2 more. All right. All right. So look at this for a minute. All right. Some people say A. Some people are saying C. Nobody says any of the tropics. And people are saying D. I'm going to run it again. Look at that answer. Okay. Yeah. And let's see if it stays the same. We get more of a consensus. Thought there was one more. Yay. All right. Yeah, that's better. So, okay, yeah, it's weakening at 66, but it's really the weakest at the North Pole itself. All right, so very strong at the equator, weaker, 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 very weak. Right? And so it's really weakest at 90 degrees. That's the best answer. Although, yeah, the aurora borealis does kind of occur there, so I can kind of see people putting that answer. All right. All right, so the best answer would be D. And thanks to the magnetosphere, yay, we actually are able to retain our atmosphere. Again, if we didn't have the magnetic sphere around us, we actually wouldn't have liquid ocean or atmosphere. And so we need those. And a lot of people don't know what our atmosphere is made of. So I just wanted to ask you guys, do you know what our atmosphere is mostly made of? There's 2 things.
Nitrogen.
Yeah, a lot of people don't know that there's nitrogen in the atmosphere. Yes. So most of our atmosphere is nitrogen, right? And so Marshak shows nitrogen as the most abundant gas. We have a lot of oxygen, right? And what's really interesting, no other planet has this. And so we're kind of in a disequilibrium with other planets. And so it's really interesting. You can see that life has impacted a planet. And so when we look to other planets, we're looking at atmospheric contributions to see if kind of there's a wonky concentration of something like oxygen there. And so that's how we're looking, one of the ways we're looking for life. And so it's really important to understand that we have all of this nitrogen and some oxygen. So these are the really light things. And our atmosphere does have some other gases, carbon dioxide, which is really important. Some of these other greenhouse gases that keep us warm. Without them, we actually wouldn't be very temperate. We'd be cold, right? And the atmosphere thins away from Earth. Just like I said, if you go 60 miles above Earth, most of the atmosphere is gone. So most of it's here, where we are. And it just thins continually as you go up in space. Right. And there's a lot of different layers so there's a lot of characteristics of the atmosphere. You don't have to know that. Oh, that came in late. Oh, well, Earth is differentiated and it's different. That's the important thing. And so I just wanted to show you, this is the atmosphere of the 2 nearby planets. Venus, you can see mostly carbon dioxide. Mars, mostly carbon dioxide. We're very different. We have mostly nitrogen. Right? And so we know this is the effect that life has had on Earth. Right? So we're very different. And thanks to the magnetic field, we were able to keep a lot of these volatile things in our atmosphere. And so I want you to understand that Earth is very different and it's very differentiated. This differentiation actually contributes to Earth's topography. Right? And so that's what we're doing in lab this week and some of next week. All right, and so because Earth is differentiated into different parts, the heavy stuff down low, the light stuff up high, actually at the Earth's surface, the light stuff goes up high and the heavy stuff goes down low. And this is actually what creates all of our topography, right? And so we're doing topography, and where does topography come from? Well, it comes from differences in the composite of Earth's crust. So the low stuff is heavy, and the light stuff the high stuff is light, right? And so the light stuff is our mountains. This is all of the silica, the quartz, right? some of the metals that have made it to the surface, so this is what's coming out of the mantle right now, it sits lower. There are more metals in the seafloor, right? So it's heavier. Right? So our topography is explained because of chemical differentiation. And so we have continents and we have oceans. All the low points on Earth, this is all mafic, this is all iron basalt stuff, right, that's coming out of the mantle. All of the continents have been here a pretty long time. Right? They've been here for billions of years, so we never lose continent. We make some more over time, but most of them were made 3 billion years ago, and they're very light. This stuff just spewed out of the mantle very early on. So it's very, very, very light. And if we take Earth, so I just take Earth, I take all of this whole thing, and I just grind it up in a blender. You know what it's made of? So I put it into a machine and just said, give me the top 4 elements. Magnesium. So Earth as a whole, the meteorite is these 4 elements. If we ground it up, this is Earth. Oxygen, silicon, iron, magnesium. If I go outside, if I pick up a rock at Earth's surface, what do you think it would be?
The silicates.
We still have light, aluminum foil, light. I'm probably missing sodium. What's the alpha phenocomate? Calcium. Yes. So Earth's surface is different chemically than Earth as a whole. And that's one of the things that's causing the density stratification. So a lot of the heavy stuff, most of this is in the core, in the mantle. A lot of the light stuff, think of how light, like the sheet of aluminum is, your can of soda. Calcium, potassium, magnesium, sodium, these very common elements. They're all here because they're very light, right? So chemistry-wise, Earth is mostly these 4 elements. So we have Earth mostly made up of iron, oxygen, silicon, and magnesium, right? So that's most of Earth. Everything else is like everything else. But at Earth's surface, we have a lot of that everything else here, right? Right? So on Earth, these elements are not distributed homogeneously throughout. Right? A lot of the heavy stuff is in the core. A lot of the light stuff is at the surface. And so the crust is Oc alpha canicomag. So it's oxygen, aluminum, silica, iron, magnesium, calcium, sodium, and potassium. All right. So this little grind, you can think of it like an apple peel or an eggshell, right? Are this chemistry. If you go into the mantle, you have just more MgFeSi, right? So you're losing a lot of this stuff, right? So this mantle is mostly peridotite. It's usually a magnesium, iron, silicate. And you'll see it's a beautiful green rock. You'll see it in lab. The core is mostly iron and nickel. And we know this by meteorites and by density. Right? It has to be nickel in there. Right? And so Earth's crust is very different from the whole bulk composition in this moment. And that it's silica, oxygen, aluminum, iron, calcium, sodium, potassium, magnesium. You don't have to remember all of those, but just understand that there's some kind of differentiation. All right. And so this also makes sense when you look at the types of rocks that we find, especially the igneous rocks, that most rocks on Earth are silicates. That's why we spend a lot of time going through the silicate minerals and the silicate rocks. And there's 4 different types of silicate igneous rocks, and they differentiate mostly by where they are in Earth. At the surface, we have a lot of the felsic rocks. These are the pink granites. They're mountains, right, the highest points. We have some intermediate where you have mafic ocean crust interacting with continental crust. So you get the andesitic, the Andes, where you have the salt and the granite mixing. The basalt is the seafloor. This is mafic. And ultramafic is the mantle. That's where you have the iron, the magnesium, silica. All right, and this is the peridotite. And it's very rare. So sometimes magma comes up when volcanoes explode, and you'll get a piece of the mantle, and that's how we know what's down there. But it's very rare to see it, right? And so what sits higher in Earth? Is it higher in Earth? The light stuff. It always. Right. So as you get more dense, you go more into Earth. Right. So the light stuff is high, and the dense stuff is down deep. And so the peridotite is all this mantle. And the lower stuff on the top of the Earth is mafic seafloor, and the very high stuff, the mountains, are the granite. And so just remember that Earth is density stratified, very similar to the solar system. Right? That makes sense? So I'll see you guys on Tuesday. Have a happy Labor Day. If you have any problems getting on to SmartWorks, let me know. Also remember that next week is a virtual lab. So we're going to send out that assignment. We don't go to the lab next week, and I'll remind you. Let's